Hello and welcome back to Calculus 3. We are starting chapter 16 on multiple integrals, multiple integration, which means double, triple integral. How many of these can you have nested? As many as you want, or as many as you need. You know that you can take the second and the third and the fourth and the fifth derivative, and in a sense those derivatives are actually nested derivatives. So going back to derivatives, if you are supposed to find the second derivative, you are looking for first derivative twice in a row. So you are probably used to the notation for derivatives. So just going back in time a little bit, I'll put Calc 1 again. If you talk about the derivatives, you have the first derivative, which you also denote as y prime, and the best notation dy dx. Now the second derivative, which was denoted with a double prime, was d squared y over dx squared. And what this meant here is that you are applying the differentiation operator, which is everything without this y, you are applying it twice. So if you are supposed to find the second derivative of, let's say, 3x to the 9th, you would first apply one derivative to it, and then you would apply another one later. So 9 times, so you copy the front operator derivative, then the derivative of the inside. So this is the thing that you are working on first. It is the first derivative inside that it's done. So that's going to be 27x to the 8. There we go. And now you have to take another derivative. So technically you are working on two first derivatives, one after another. And this is going to be, what, 160 plus 56 to 16, x to the 7. So now we are going to deal with the integration the same way. I'm going back to Calc 3. We are going to have what we call a double integral of a function, let's say, I don't know, 4x squared plus 6. And I'm going to put dy dx. We will see what this means. Now we are going to use the limits here. So 0 to 1 and let's say 0 to 2, just because we can. So just as before, you see that over here, this differentiation operator was used, that was closest to the function you operate on, was used first, and then the second one on the outside, which is this one here, was used later. We are going to have the same deal in here. I'm going to do the inner integral first, and as you can see, the inner integral operates only in respect to y. So I am observing this 4x squared plus 6 as a constant, the whole thing as a constant, because it is a constant in respect to y. And I will integrate the inner integral first, which will give me 4x squared plus 6 everything times y, computed from 0 to 2, and I still have dx to deal with later. So all I have done is I completed the inner integral, which is in the blue box. Now we will compute that integral. That's going to be 2 minus 0 for y. So 4x squared plus 6, and then we have 2 minus 0. Still have the dx. And finally, 0 to 1, I can multiply this in, let's say, 8x squared plus 12, everything dx. And now we deal with dx. So this is now calculus 1. The integral of this would be 8/3 x cubed plus 12x, computed from 0 to 1, to give us 8/3 plus 12, which is 8 plus 36 over 3, or common denominator, gives us 44 over 3. So to deal with the double integration in terms, or triple, or if you have 17 of these integrals, doesn't matter, you always go all the way in the middle and you work your way out. So you will start with whatever is integral is in and then work your way out. And learn to set them up. Now the title. The title said rectangular region. We usually call it region R. Not the double bar R, just the rectangular region R. So rectangular region R is referring to domain. If you remember, you have that f of xy, right, z is equal f of xy, where these two guys over here are the domain. So if I am to draw some kind of a rectangle, here, this would be my domain from x1 to x2 and y1 to y2. This is region R, which is my domain. Your cookie cutter, in this case, is in shape of a rectangle, and once you press it into a dough, it pushes all the way down to the table, presuming you are making cookies on a table, and it will have these straight edges, just like the edge of the desk, cuts all the way straight down. Now the top of this function, that it's built on top of this rectangle, you can think of a surface of a printer over there, or surface of your desks, or whatever, right? You guys have some kind of wavy surface on top of this R, and that wavy surface is given by f of xy, which are your collection of your z's. So when you look at this, you see that your representative rectangle that you know as dx, right, is going to shift from left to right. And you can set up a general integral. This is the general formula for the integral. But you can't compute anything with this. This is just show. What this means is double integral over rectangular region R, and the order of x and y is not specified at all, where dA equals dx dy or dy dx. Not specified yet. So now, if I am calculating a double integral, then since dA is like a delta area, dx times dy, and then times f, it should give me a third-dimensional entity called volume. So if I have some kind of rectangular domain over here in my xy graph, so this is going to be my x1, this is my x2, it's my y1 and my y2, and those would be the limits that we use. Somewhere over here, when we draw representative delta x and delta y, we are going to get this little square. Doesn't have to be a square, but square. This square, let's make it larger. Has delta x and delta y as its measurements. So that's your dA. And this is where we learned that dA can either be dx dy or dy dx. And you will pick those. In some cases, they will be interchangeable and you will be able to. Right? So this is what the domain looks like. Now, this is going to, go up and create some kind of a, there's some kind of a function on top. It's whatever the top is, right? We don't know. This top over here is given by z equals f of xy. And you will have this little area. So now we know that as we use more and more and more of these, as the partition gets better, your approximation gets better. So I'm going to quickly show the textbook idea. Partitioning is done the same way as in calculus 1 for 2-dimension. Now you just have 3 dimensions. So here we go with the image. So if you take a look at the image all the way to the left, you see that you have 16 of these French frises, right? You have a 4x4 grid, so there are 16 of them, and you can see that the top is not really well approximated, right? But then as you go from 16 to 64 to 256, right, you go from, I don't know, French fry to some type of pasta to angel hair, I don't know, and then you have, I don't know, all the pastas in between. And then you have this one. Now, the one at the end that has the exact volume is the one that has infinitely many of these divisions, because your delta x and delta y are both infinitely thin. They can fit infinitely many of those, and then the top becomes smooth, no errors, no pixelation to it of any kind. It's just one smooth surface where, when you do the calculation, the whole thing becomes perfectly smooth, and the volume would be exact volume. So now, if you think about it in this way, right, we can write our volume integral for the first time, writing it as, again, this is not the way we compute, this is the way we understand. So the integral of xy dA will be given with the good old limit delta goes to 0. I'll explain that. Summation of, this is f of, they use xk, yk, fine. K goes from 1 to n, and it was sent to infinity eventually, and delta A k. So this was the exact formula. And as you can see, it follows exactly what the formula in calculus 1 was. If you remember, the Riemann integral from a to b f of x dx was given by the limit when n shoots to infinity, 1 to n on the summation, and you had f of, they call it ci delta x. It's the same formula, except now you have xk, yk. I used i's, you can use k as well, so here, call it a ck. It's fine. Right, so it's the same one, except now you have one more dimension, so your input in the domain is no longer just a line, it's actually area, and then times the height towards z in z direction to give you the volume. So it's the same deal. And now we can move this into the formula that you actually use to compute integrals. Volume is equal to, and now you're going to have either dy dx. Now, if the y is the inner integral, then the inner limits have to be y1 and y2, and the outer integrals have to be x1 and x2. And or you're going to have the integral, which will be, dx dy. Now the inner integrals are x1 and x2, and the outer intervals are y1 and y2. Now this is the formula which we are computing. This is to set up and compute integrals, and as you can see, the limits are just numbers everywhere. The next lecture changes the inner limits into functions, and then you are able to have all kinds of different shapes, not just rectangular bases. I will get there next time. So I have all of this. So what I'm going to do is first solve one more of these vanilla problems that have no applied context to it, so just shoveling numbers. Let's integrate 2x plus 3y, and we are integrating dx dy this time. So this is just given to us. Again, is the integral in x first. Right? We are integrating in respect to x. What happened?
I was just trying to read what you're integrating from. Is that a 1 or a 1? It's a 1. Sorry.
All good. How about now?
That's better.
Here. That's the best I can do. All right. So we're going to integrate the inner integral first. It's in respect to x, and it goes from -2 to 1. All y's are going to stay constant in this case. So we have the outer integral 0 to 3. We're not touching that one. The integral of 2x is just going to be x squared plus 3xy, and now all of this goes from -2 to 1, and we still have dy to deal with. So 0 to 3. When I plug in 1, I get 1 squared minus 3y minus -2 squared, and then minus 3 times -2 times y, and I still have dy. So if you carefully look, I replaced every x with 1 in the first round, and then minus, and then -2 in the second round. So now we need to compute all of this mess, and then integrate one more time, and we're done. So this is 1 minus 3y minus 4 plus 6y dy. It simplifies down to -3 plus 3y dy, and finally we have -3y plus 3/2 y squared, computed from 0 to 3. Plug in 3, we get -9 plus 27 over 2, which is 9/2. So this problem had no context. It was just here, integrate, and walk away. We know it had the rectangular domain because the limits on the integral were all numbers. And if I want to graph the domain of this function, I just pick up what the values are. Right? So to graph the domain, and that's one of the very important skills, we need to know what are the limits. Then over here you have some blah, and then you have dx dy. This never plays a role in the domain. Your domain is 100% explained by the limits and the order you have over here. So now I can draw this and say the outer integral is in terms of y. So these are the y numbers, 0 and 1, 2, 3. So I have these two construction lines, this one and the x-axis. And then I jump into the x limits, which are these two, which are -2 and 1. So this is the domain. The integral lives over this square because this is a 3 by 3 square. Now this skill is going to be very important later. So the more you practice now with the cheapest possible situation you can have, later on in a chapter it's going to get much better. Let's take a look at another example. Now this time it's going to be much more interesting. We can think of this as a skateboarding ramp or one of those for bicycles, you know, where kids go to knock out their teeth. So we're going to have something like this. It's going to have a curve over here. Okay. There we go. Now they give us dimensions for this on x-axis. The dimension is ln4. On the y-axis, the dimensions are 2. And over here in the back, you can't see it, but it's there. Is going to be -2. And the surface over here is given as z equals e to the -x. It's a cylinder. What is the volume of this slob? how much concrete do you need to pour? How much concrete would it go in this much? Right? Let's say this is a ramp you are constructing. So if you think about this, I mean, if it's 4 meters wide, let's say that's twice my height. So it's a fairly wide ramp. So, or you can do 4 feet still, shorter, but whatever. So now what do? Well, the first order of business is to see what the domain is, because domain will give us limits. And we draw a domain on a separate graph. Now the domain is xy, and you have to be very careful to read where the values are on the graph, on the picture, to transfer them to the domain graph. Observe that y is the value that goes from -2 to +2. That's happening on y. And then your ln4 is somewhere here. So let's put there, ln4. So here's your region. It's this rectangle, and when I am setting up my volume integral now, I know that I am integrating e to the -x. I have a choice of working dy dx or dx dy. Now, the greatest thing about the first section, first lecture, is that it doesn't matter which one you pick, but let's work on dy dx. So as soon as you pick dy dx, then you are locking y limits to be the inner integral, because dy is the inner and dx is the outer part here. So dy, we collect its y limits, and then for x, we collect its x limits 0 to ln4. You have this dx vertical representative rectangle that will swipe from 0 all the way to ln4, and then dy is the vertical one, which would go from -2 to the bottom to the +2 on top. So that's the way we set these integrals up. So what we do is the integral, the inner integral, and that one will just give us y from -2 to 2, and we still have dx 0 to ln4 to deal with. When we plug in the upper, we get 2e to the -x minus -2e to the -x dx. That gives us 4 integral e to the -x dx from 0 to ln4. So 4, this is integral e to the -x divided by -1 from 0 to 4. That's -4. And over here I have e to the -4 minus e to the 0 is 1. And if you multiply negative inside, you will get 4, 1 minus, and I'll just put 1 over e to the 4. So we can see that the volume is a positive number, right? You have, so the negative in front of the 4 is the one that swaps the order. So that's why it's 1 minus, and the negative on 4 is the one that pushes e to the 4 in denominator. So now we have volume. And you can go and calculate, the volume if you want to. So to integrate these, work on the inner integral first. The most important skill for this lecture is to understand, right, to learn and to understand that the inner integral is your calculus 1 integral you all know and love. And the limits for that integral have to be on the axis where the whatever variable you have within the d part. So if it's dy, you better have y limits go with it, and dx will have the x limits go with it. Integrate the inner first, copy the outer integral. As you can see, I copied exactly what it is, and just computed everything inside, and then rinse and repeat one more time. Clearly, the first lecture in 16.4, I believe, when we do the triple integral, we are going to do the same procedure, but you will have 3 integrals in there. You do the inner one first, then the middle, and then the outer. Now, the following theorem works only for double integrals over rectangular regions. So this theorem works only for this one, and then it will work also for triple integral rectangular regions, but that's it. The theorem says we can interchange the order of integration. Guys, this works only in this section, and then for the rectangular region integrals for triple one. Only for rectangular ones. Yes?
When you say rectangular, do you mean like rectangular coordinates or rectangular like shapes?
That's going to be confusing as we move on. So rectangular in this case will mean you just have numbers in limits. The next lecture will have functions in them, and you can't swap them. So rectangular means you have rectangular domain, and at the same time it's rectangular coordinates. But when we move to polar, the polar integrals, double integral, which is the next lecture, I believe, no, after exam. After exam, I think first lecture after exam is going to be polar, double integrals. We're going to call a rectangular those that have numbers in their double integral limits. Because the one integral will be for radius, one integral will be for angles. And if you have numbers everywhere, those will be called rectangular, even though it's a polar integral. So rectangular simply means you have all of the numbers as your limits, and you can interchange them. If you have a function, which is our next lecture here, and also in polar coordinates you can have functions in limits as well, in that case your integral will no longer be called rectangular. We will call it a general. So rectangular right now has a double purpose, the word rectangular. But throughout the whole chapter, word rectangular actually means all numbers everywhere for all limits, no functions. And then if you have functions, we call them general regions. So we'll deal with that. But for rectangular, that's a very good question. But without having at least two more integrals to kind of sort that all out, it's kind of a little bit difficult to understand. But yes, so right now it means rectangular domain, but it will mean more. So we can interchange order, and that I will going to say that the integral a, b, c, d of some function f of x, y, dy, dx is going to be the same as integral c, d, a, b, f of x, y, dx, dy. This is exclusively for rectangular integrals, meaning just numbers as limits. This will not work in the next two sections. This will not work. We can interchange the order of integration. Now, why is that so? Well, if I have a rectangular region, right, you have a rectangle, area of the rectangle, it doesn't matter whether you use a times b or b times a. It's still the same area of the same rectangle. So, translating that to your 3D integrals to find the volume, if your domain is rectangular and you will be multiplying by the same wavy top, it doesn't matter whether you go a times b times z or b times a times z. It doesn't matter. It's going to work out the same. So rectangular regions, we can interchange the order. Now, changing the order of integration sometimes is convenient, sometimes is necessary, and sometimes is completely useless or pointless. So this integral here, it's useless to exchange the order of integration. Doesn't matter. Does not accomplish anything. Doesn't make a problem easier, faster, anything. If you swap the order of integration for this particular problem, there is no difference. But in certain problems, if you swap the order of integration, you might avoid a more difficult integration technique. Or you might actually gain, by integration, you might gain something that it's necessary for you to integrate further. And those are my favorite examples, obviously, right? So behold this. Look, let's say you have to integrate e to the 4x squared, right? And you have double integral dx, dy, and they all both go from 0 to 1, just to make it simple, right? So let's say this is your problem. This is not going to actually, a little bit, this is not going to work here because of the numbers. No, this has to be done in the next section. Sorry, guys. Sorry. Because, look what happens. You can't integrate, right? U sub doesn't work. Nothing you learned that works here. Nothing, right? Now, if these are different, well, you know what? I'm going to talk about this next section. I'm going to come back and talk about this next section because that's when it's meaningful. Right now, it doesn't matter. Rectangular integrals are just way too easy, so we don't need this. Let's solve one more of these and then take a look at the section where we actually have to think a little bit. So one more of these, guys. Let's see what they give here. Something nice. We haven't had any trig, right? problem 34. Let's solve this one, and then we'll go and do some interesting things. So double integral over rectangle region R, the cosine of x root y dA, region R is given as set of all points xy such that x is in between 0 and 1, and y is in between 0 and pi squared over 4. All right, that's the integral. So you have to write the integral, put the limits, put the order dx dy or dy dx, whatever you want, and get. Let's take a look at this. So, as I said, it doesn't matter which one we do first. So we can just do, let's say, dy dx. Most of the time we work dy dx if we can, but it doesn't have to be that way. So the y limits are the inside limits, so 0 pi squared over 4 and 0 to 1. That's that. Now, integrating cosine in respect to y. So how would you integrate cosine? Yeah, but subbing what? Do what? Okay. Have you done it?
I did by dx.
Oh, you did dx dy. All right, let's do dx dy then. That will swap these guys. So if you do, well, then the square root of y is the okay. So we are integrating in respect to x. Square root of y is constant in this case, right? If it's a constant, we get to copy it. So we have the integral. Integral of cosine is sine x root y divided by root y, because that's the constant. And then you have the 0 to 1 limit, 0 to pi squared over 4, and the y left. we have to plug in 1 and 0. The sine of 0 is 0, so just 1 would stay. And we have sine root y divided by root y dy. This is where the u sub kicks in. U equals root y. Du equals 1 over 2 root 1/2 over root y dy. I don't have a 2, so I will fix that by plugging in a 2. And this becomes 2 integral of sine u du. Now we can change our limits as well. It's going to be square root of 0 is 0. And this is pi over 2 now. Because when you plug in pi over 4 into the square root on y side to plug in or get u, you get pi over 2. This is negative cosine u, negative 2 cosine u, pi over 2, and that's a negative 2. Cosine of pi over 2 is 0, minus 1, and the whole thing 2. Good. Nice. So let's take 2 minutes break. After this, we're going to take a look at a little bit more interesting case.